Okay, as Dr. K said, I'm Matt Heflin. I worked this summer with Dr. Linder. Our project was to find a method for inference for correlation in a bivariate normal model subjected to type 2 censoring. So a brief overview of what I'm going to talk about. I'm going to start by talking about sampling distribution of correlation. And sampling distributions in general are a really important concept. I want to say that now because they're necessary for statistical inference about a population. So you're asking a lot of your statistical questions are answered by sampling distributions. Then the second thing we're going to talk about is type 2 censoring. Then I'll talk about how we improved inference for correlation over a typical method. And then I'll go over the results. So correlation is a measure of how related two variables are linearly. Population correlation can be gotten at if you have the data for an entire population and you calculate correlation. Problem is, in practice, we don't get data for an entire population of interest. So we get a sample instead and calculate correlation with that to get sample correlation R, which we use to estimate the true correlation or population correlation rho. So to introduce the idea of a sampling distribution now, we're going to consider an example. So let's say I claim to be an 80% free throw shooter. You're skeptical, so you want me to shoot 100 free throws and see how many I can make. But how many do I have to make to convince you? If I only make 76, are you going to call me a liar? But if I make 80, does that mean I'm telling the truth? Well, the problem with that method is that what really matters is, can I repeat? Because if I really am an 80% free throw shooter, I might have a bad day and shoot less than one day. But another day, I might have a great day and shoot more than 80. So the idea is it's the distribution really that matters. And the sampling distribution captures this information and allows us to ask questions and answer questions such as, given a sample statistic, what sort of range is the true statistic in? How confident can we be that the true statistic is in a particular range? So, and we care about this because we can use it for inference in that sense to create confidence intervals. So here's some examples. These are histograms. They're a good visual approximation to a sampling distribution. The top one is for true correlation equal to 0. The bottom one is for true correlation equal to 0.7. Notice how it's skewed to the right on the bottom one. Now I'm going to introduce type 2 censoring through another example. So consider a college that has 5,000 freshman applicants, and they're only going to accept 1,000 of them. But they're going to base this acceptance on a performance measure that they've designed. And the idea is the top 1,000 scores on this performance measure, those students get in. But they're also interested in how well this measure predicts future college success. So you might think of doing a statistical study where your x variable is the performance measure, score on the performance measure. The y variable is a student's GPA after the first year of college. And you'd be interested in the correlation between x and y. So why is this type 2 censoring? Well, it's censoring in general because you only get to see 1,000 of the data points. We don't have data for the other 4,000. We don't get to see the 4,000 that weren't admitted. We don't get to see their GPAs. In particular, it's type 2 censoring because the number of observed data points was predetermined. The college already knew they were only going to accept 1,000 students. And then finally, this example sort of shows how censoring is carried out in the sense that the x values, the performance measure score, were ordered, and the censoring was based on the x values, whereas the y values just followed their particular x value when ordering occurred. So background on the actual project we did this summer. So in general, the sampling distribution of correlation is mathematically intractable. So there's no nice equation for it. And censoring further complicates this. So if we want to use it for inference, we're going to have to come up with some sort of approximation. As it turns out, when there isn't censoring, there is an approximation, or a transformation rather, called Fisher's Z transformation. It was discovered in 1921 by R.A. Fisher. And it transforms, well, 1915 and 1921 sort of built on himself. But it transforms sample correlation into a statistic with a roughly normal distribution. And since we know a lot about the normal distribution, we can carry out inference for this new statistic called Fisher's Z and then translate it back into into inference for correlation. But since we're considering a case with censoring, we started with that as a baseline model and found out that in many cases the transformation is inadequate. And so we considered a modification that involves shifting this normal percentiles with a regression model for error that we obtained through simulation. So our assumptions, we're in a bivariate standard normal setting, so 2 variables, both with standard normal distributions. N is the size of a full sample, P is the size of the censored sample, the sample we actually see. Alpha is the corresponding percentile of whatever distribution we're looking at. Rho is population correlation, and R is sample correlation. Z alpha is the alpha percentile of a standard normal distribution. This F inverse notation is just shorthand for alpha percentile of the distribution we're looking at. And then these are the cases we considered at the bottom here. So I mentioned a lot about Fisher's Z so far. This is the actual formula for it. And it has, the statistic has mean and standard deviation given there. We actually used, and we're interested in the sampling distribution of a standardized version of this. So we were using a standard normal approximation as our baseline. And that's the formula for that. And so to talk about inference, we considered 2 methods. We considered the standard normal approximation. We considered our modification. And one of our major, the one I'm going to discuss here, one of our major performance measures was coverage rates for 95% confidence intervals for Rho. And so what I mean by 95, before I go on, what I mean by 95% confidence interval and for coverage rates, you could consider doing a simulation where you simulate a lot of different confidence intervals. And then in order to get the coverage rate, we would expect, we figure out how many of those actually capture Rho, and that gives us our coverage rate. And if our assumptions hold, then we would expect that coverage rate to be around 95%. So at the top there in equation 3 is a confidence interval formula for zero, not Rho, but I didn't want to do the one for Rho because it's complicated. It involves using the inverse function for Fisher's Z, the function I showed earlier, the inverse of that. So, but just know that that's how we got the confidence intervals. So table 1 shows coverage rates for these unmodified intervals, just using the standard normal approximation. And we find that no censoring or if there's only a little bit of censoring, or if Rho is small, we actually get coverage rates near that nominal 95 level. But as we come across the table to the right, coverage rates deteriorate significantly as Rho increases, especially for moderate censoring. In particular, for Rho equals 0.9, N equals 30, and P equals 13, you only get a coverage rate of 72%. To deal with this, to deal with these inadequacies, we introduce our model. So a regression model for absolute errors, defined up there. And so given NP and alpha, we propose that the true percentiles, which we obtain through simulation, because we don't actually have the distribution, be approximated by standard normal percentiles minus an error function, which is given in 4. So here's the confidence intervals for the modified standard normal approximation for using that with the new percentile estimates. And this is once again for 0, and we translate them in the same way I discussed earlier. Table 2 shows these coverage rates. So for n equals 10, we find that they're all near nominal, but that was just the same case when we just used the standard normal approximation. But when n equals 20, so both models work well in that case. But when n equals 20 or 30, results depend on Rho. So for 0.1, Rho equals 0.1, the unmodified is actually better. But as Rho equals 0.3 or higher, the modified is better. And the magnitude of the improvement increases with Rho and is best for moderate censoring. So here's a graphic that shows it. I'm probably not going to have time to really go over it. But if anyone has questions about it after, I can go back to it. This is for n equals 30. So in conclusion, the modification is a significant improvement for moderate censoring and for large values of Rho, but it's not as useful for smaller values of Rho, and in fact, we may be better off using just the standard normal approximation suggested by Fisher's transformation in that case. And then for the modification, coverage rates are closest to nominal for moderate Rho, so between 0.3 and 0.7, say. And finally, we also considered We also considered a confidence level of 90% and 99% and higher values of n, and we found the same sort of trends. So it looks like I'm out of time, and I would like to thank my mentor, Dr. Linder, for putting up with me this summer, and I'd like to thank the NSFRU program and Ohio Wesleyan University for making this opportunity possible, and I'd also like to thank Vivek Sampath-Kumar, who was my predecessor on this project. So thank you. Are there any questions?
Okay, this paper is now open for discussion.
Yes.
Can I ask a question? Can you back up one slide, 2 slides, and explain that plot?
Yes. Thank you. Okay, so this plot is for isolating n equals 30, and it shows coverage rates for both the modified and unmodified confidence intervals. So the dots are for unmodified, and the triangles are for modified. And the solid line in each plot is the nominal 95% line. And each plot is isolated on a value of rho. So at the very top left corner, we get rho equals 0.1, and then going from left to right and going down corresponds to increasing values of rho. Notice in the first plot at the top left corner how the dots are the ones right around the line, and the triangles are below. So unmodified is better than modified. But as you go further down, the gap between, well, first off, at 0.3, they're about the same. But then as you go further, the gap between the triangles and the dots is much, much larger. And the triangles are the ones, the modified is the ones that's right around that nominal line. So it's just a graphic that kind of shows in general what we saw. Anything else? Yes.
Oh, no. I thought I saw you. I guess not.
I just wondered what, when you said, you mentioned moderate censoring. What does moderate mean?
Okay, so we considered, and I didn't really explicitly explain the cases as I have the notation up there. We considered values for p, so the actual sample size you see, running from 4 all the way up to n. And so for moderate censoring, usually meant somewhere in the range of 50% censoring about. It's not a perfect, perfect science, but so for moderate censoring, so like p equals 13, it's a little less than 50%, around 42% censoring. So, or 42% seen, so almost 60% censored. So that's usually what was meant, somewhere around that 50% line.
Any other questions? Now let's thank our speaker again.